So let's start with Cristiano.
Yeah.
Yes.
Yeah. So, hi, everybody. Would like to start by thanking the organizers for the kind invitation and for my horrible behavior that I answered the very last minute, and they managed anyway to arrange something. So thank you. So what I'm going to speak about something new, bit unconventional. So probably you never heard, so maybe you're curious about that. So it's something that we started to call the finger of the observer effect. It will become clear in a second what we mean. And this is work in collaboration with a PhD student, Mohammed Yusri El-Kashab, who's about to finish and will be on job market. Very good guy if you look someone in simulations theory and so on. And Daniele Bertacca is a senior scientist in Padova. So you heard quite a bit about this already in the previous talk, so I'll be very quick here. Soon after the discovery of the microwave background, Dennis Sharma, who has been many years here and was my PhD advisor, actually, so I'm always very happy to remind him, realized that if the CMB was primordial, at the time you didn't know that, you would expect to see a signature of the velocity of us, the observers, imprinted in the temperature anisotropies there. Of course, there was no way to measure this at the time, but nowadays we measure it very well. This is actually almost 20 years ago. And you see clearly a dipole pattern in the temperature anisotropy of the CMB. And if you take the latest measurements, you determine the direction of the dipole in galactic coordinates very precisely, and its amplitude as well. And this corresponds to a velocity of roughly 370 kilometers per second in a given direction. So the idea here is that the CMB was emitted and last scattered by matter, redshift 1100. And what you are measuring now is the relative velocity with respect to matter, if matter has been always co-moving in the expansion of the universe. Then, a few years later, well, almost 20 years actually, Ellis and Baldwin realized that you should expect dipoles also in the distribution of galaxies in the sky for the same reason. Basically, here is a bit different. I mean, it works through aberration and Doppler effect. And so this has been measured as well, even though it's a bit complicated because you need special samples, which are very homogeneous, very well selected, big distances. But in the last few years, people started using radio continuum selected galaxies, 1.3 million of them. And they conclude, based on this analysis, that the dipole from these galaxies has more or less the same direction of the CMB one, but it's kind of 5 sigma away from that in amplitude. It's way bigger. And here you see a frequentist analysis of what you would expect by generating fake CMB skies, and this is what they measure. So several groups here, there are just 2 found the same with the high redshift quasar or high redshift galaxies, but there is also another group who actually analyzing very similar data find nothing, find complete agreement with the CMB sky. So, these things need to be considered with caution. And so, part of the community think that these data are affected by systematic error, maybe since these are all photometric samples, there's low redshift contamination in the data. They are not really high redshift galaxies only, but sorry, I went too fast. While others take them seriously, and so start speaking, maybe we are seeing huge bulk flows in the universe, tilted universes in which there are 2 families of observers, or this could be the presence either of super horizon isocurvature perturbation, which would mean actually in this case would be the dipole of the CMB that doesn't give you the peculiar velocity because it would have an intrinsic component. So this is the situation. Skip that for the sake of time. Then we were thinking one day that People just use photometric data to do this because you need big samples at high redshift. But now we are in the epoch in which we are building big samples of high redshift galaxies with measured redshifts. And it's mostly driven by dark energy science. And so we thought, well, these are big samples covering big volumes with high density, very precise redshift measurements. Why don't we try to measure the observer velocity, so our peculiar velocity from these samples? Is possible? And actually, what is the effect of our own velocity on this data? So we started thinking of that, and I try to guide you through. It's a bit mathematical, but I will try to avoid all equations, okay? So you saw plots like this in the conference several times already. The redshift you measure is not actually the cosmological redshift because there are perturbations in our universe. And what you have seen normally is just the first two objects here, that 1 plus z you observe is 1 plus z cosmological plus 1 plus v of the source of a c, the parallel component. But if you do the calculation right, you should also put a term that depends on our own velocity, okay? And then there are further relativistic corrections if you want to account gravitational redshift and so on. So due to this, when you measure redshift and then you use your favorite cosmological model to assign a distance to the galaxy, you make a mistake. And the maps you build are not the real distribution of galaxy in space, but they're a bit distorted. And this is what you call redshift space distortions. One of the most famous effects associated with redshift space distortion is an effect that people call the finger of God effect. And the name comes from a paper by Jackson in 1971, which was entitled Fingers of God, a critique of Reed's theory of primordial gravitational radiation. And basically, he finds an explanation for these fingers of God, which is written here. This is copied from the text of the paper. The idea is that whenever you look at objects in redshift space, you tend to find kind of cigar-shaped things that point toward you. That would be the finger of God, telling you that you did something wrong. And which in reality are just, kind of spherical objects in real space that you see elongated along the line of sight just to the fact that the velocity dispersion in this object is quite high. And so this correction to the redshift due to peculiar velocity disperse them in the third direction. We will see that soon we will introduce something called the finger of the observer. And for that reason, I was introducing this. So let's take this opportunity, first of all, to remember Nick Kaiser, who has been a very prominent scientist in the field of large-scale structure, who unfortunately passed away shortly ago, just a few weeks ago, actually. And he was the father of this field of redshift distortions. He realized that when you consider the fact that you measure distances through redshift, you are actually measure the overdensity of galaxies not to be the real one, but it's the real one plus some corrections. And these corrections have to do with how fast along the line of sight the velocity change. And this is a kind of Jacobian of a mapping. You are actually deforming your volume by using the velocity as a tracer, sorry. And there is another term here that actually depends also on our velocity. And this term has always been neglected in the past. The reason is when Kaiser developed this in 1987, all the surveys were local. And this alpha, which is something has to do with the selection function of this survey, is a number over the unity. And you see there is 1 over r here. So this term drops very quickly as you go far away. And so whenever I say you have sufficiently deep survey, this term can be neglected. And for that reason, most books, even you find just the first 2 terms when you speak of redshift space distortions. But I'm going to show you that when you go to high redshift, that term is terribly important because the expression of Kaiser is not correct at high redshift. It needs further corrections. So what you want to do now is to do the calculation in full general relativity. That calculation before was just done saying, oh, I take my distance, I add d over h basically as a distance. And now you take into account that the light from a galaxy to reach us has to pass through the whole universe, and so will be bent by mass concentration, will be gravitational rest-shifted by potential wells. There are differences between the rest frames of the observer and the emitter. The observer will generate aberration. There are time delays and so on. You put everything together, and you get this new version, let's say, of the original Kaiser calculation. You see that now you have the observed overdensity is the true one minus the Kaiser correction, the one that gives the Kaiser factor in the power spectrum. But what before was a term that was going like the difference of the source velocity and the observed velocity, now it gives two different terms with different coefficients. And this is telling you that actually our own velocity leaves an imprint on the overdensity that you measure. Now, there are many details here. What exactly at this alpha function is detailed here. They depend substantially on which galaxies you look. It's something like, for those who are more used to the bias factor of galaxies, there are other bias factors which we tend to call in this field evolution bias and magnification bias. They have to do with how the luminosity function evolve over time and what's the shape of the luminosity function of these objects. Anyway, the important thing to remember here is that the observed overdensity, so the one you reconstruct from observation, is actually the overdensity that an observer who is co-moving with the expansion of the universe would measure, plus a correction, which has to do with the velocity of the person who observed the galaxy. And this correction, you see, is dipolar form. It goes like a cosine with the direction with respect you move. And it has an amplitude that depends on redshift, depending on several things. You can see here, it depends on geometry, what gives this 2 and this 3. It depends on the galaxies you look, what is this Q and this epsilon, but depends also on cosmology. You see here, there is the cosmic expansion history encoded in these coefficients. So now what we ask ourselves, okay, can I see this? For instance, the simplest statistic you do when you study galaxy clustering is to measure the power spectrum. So in this case, you want to do even the simplest power spectrum possible. You average over all directions in the sky. So it's what we call the monopole moment of the power spectrum. And you find out that what you would measure, due to these two terms, is the true power spectrum that comes from this, plus a series of bumps which are generated by this dipole term. Now you could ask yourself, are these bumps big enough to be seen? Well, let's have a look. Normally, the power spectrum of galaxy peaks around 20,000 in these units. So it will be here. And you see that now, if you go to very large scales, these oscillations are actually of the same size or even bigger. So what we have learned so far, that this impact of the fact that we move with respect to the co-moving frame changes the redshift of the objects, then changes the overdensity of galaxies, and introduces an oscillatory pattern in the power spectrum. And you can compute all this analytically perfectly. So you know this. It's totally deterministic. There is no stochastic terms. So now the question is, can I see this in a real survey? So in order to do that, you need to build, mock catalogs, so fake surveys that you build in your computers, which have all these effects inside. And these are normally not included in normal embodied simulations, which are fully Newtonian. So some years ago, with some other students, we built a code, which is called LIGER, which is light cones using general relativity, which actually takes the output of Newtonian simulations and introduce all these corrections, ray traces through the simulation to propagate light rays, and builds a light cone, a proper light cone, not like the cheap light cones are often done in galaxy evolution computation, in which you replicate boxes and so on. There is no replication here. You need huge boxes, so it's a bit numerically heavy, but in the end, you can build artificial surveys. So this is an artificial Euclid survey, for instance, with the Euclid imprint that cover big fraction of the sky. And this code is free. Actually, you can download it from this website. So we use this, and we produced 140 mock skies in which we have these effects. We observe, trying to mimic surveys which are about to come, and see whether we can measure them or not. So this is the result, for instance. So the top line refers to a survey that selects galaxy in H alpha, so in this emission line, which is appropriate for something like Euclid or the Roman Space Telescope, while the bottom line selects galaxy with H1, so the 21 centimeter line of neutral hydrogen, and so is appropriate for SKA. What you see is what you measure with the scatter among the 140 mock catalogs, and the dashed line is what would be the power spectrum without this dipole due to our peculiar velocity. You clearly see they are different, and now you can ask yourself, with what signal to noise you will be able to distinguish them. And you see that when you have a full sky survey, you get to signal to noise of 7 or so. With something like Euclid, just cover more or less a third of the sky, you get a signal to noise of 4, which still not too bad. Okay, so the model is perfectly accurate. Now you might ask, like many of our colleagues asked, so it's a natural question to ask, sorry, why are you wasting your time here? We know how to go from one frame to another. Just correct the redshifts and everything will be fine. You just go to the CMB frame by changing the redshift. So you can try to do that, and then you find out from your mocks that often actually the effect is bigger than before. So we don't have a time to make a poll, why is that? But I tell you the reason. The reason is when you correct the redshift to go to redshift frame, you just correct the redshift. But the peculiar velocity also affects the luminosity of the galaxies and even moves them in the sky. And so all these other effects you are not considering. And so you don't cancel fully the effect. Again, you can do a full analytical calculation and you find what is the effect of going to a different reference frame. And now you can actually play with this and try to shift galaxies into different reference frame, fit with the model the power spectrum you measure, and see whether you can retrieve information on, for instance, our peculiar velocity. Now you can have 3 possible objectives. If you have very low ambition, you say, I already know the peculiar velocity. I know from the CMB, so I don't have to measure it. Then what I can do with this? Well, you could measure these bias functions that characterize your galaxy population. Okay, it's not so interesting, so I won't show anything about that. If your medium ambition is, well, we set priors on cosmology, we know. We measure these bias functions from the luminosity function of the galaxy, and we set constraints on the peculiar velocity of the observer, for instance, to test whether these claims from the quasar samples are appropriate or not. If you are very ambitious or maybe mad, the first time I spoke of this, a guy told me, are you crazy? Is actually to try to spoil this logarithmic derivative of the Hubble constant in these functions and try to make cosmology out of that. So how does it go? So we have these 140 skies, which are much more what we will have in reality. In reality, we will have only one when these skies are measured, when you have Euclid. No, here we have the luxury to try with 140. We did a full Bayesian analysis of all these cases, and now the issue is, can we measure our peculiar velocity from this effect? Here are the results for the H alpha survey and the H1 survey. The black line is the true velocity, and the red error bars of what you recover from this analysis. You see, you measure the amplitude very well. The measure is unbiased. With SKA, you would do the same. And this is the error bar you would make for the direction on the sky. It's not as good as the CMB, but it's not even as bad, and it's much better than the quasar samples. You see here these triangle and crosses, actually the measurement from these quasar samples I showed at the beginning. Now, the ambitious goal, can I use this to measure cosmological parameters? Well, now it depends a bit what you want to fit and what you assume you know. So suppose you like the lambda CDM model. In this case, you only have one parameter to fit here, which is omega mater. And how would I get omega mater? This time you assume that the velocity you already know from the CMB. These are the measurements from the 140 Mach sky, and the gray band is our current measurements of omega mater from the CMB. So you see, this is not worse than the CMB on omega mater, okay? Then you can say, well, omega mater alone, come on. I mean, let's put at least some equation of state of dark energy. Now is the simplest case here in which we just use a fixed value of the equation of state. And in this case, the measurement gets very degenerate between omega mater and the equation of state. But if you identify these bananas, a bit like you do in S8, you can define a new parameter, which is a nonlinear combination of omega mater and the equation of state, and thus is once again very well measured. So, okay, looks fantastic, but can I do it? Well, there is a caveat. I don't know if you paid attention, but when I was looking at the K values in which you see these oscillations, they're very low. Okay, so we are speaking of K values of 10 to the minus 2, 10 to the minus 3, depending on the redshift. They get lower and lower when you go to higher redshift. And measuring clustering from a redshift survey on such large scales is a bit difficult because you observe different patches of the sky at different times, and you need to make sure that your selection effects are actually constant over time. You have dust correction if you are in the optical or near infrared. You need to make sure you know very well. But let's say this is an observational problem. In practice, if you manage to get these systematics under control, this is very promising. So let me conclude. We showed that our peculiar velocity modifies the redshift size and luminosity of cosmological sources. This was already known. I mean, it's nothing new. But what is new is that if you do the full calculation of redshift space distortions, there is a term that depends on our own peculiar velocity that we call the finger of the observer effect or photo effect. This generates an oscillatory pattern in the monopole moment of the power spectrum. You can't erase this by changing the redshift, correcting the redshift, going to the CMB frame. Actually, you make it worse. And that is measurable with the next generation of redshift surveys. And if we manage to keep under control the systematics in these surveys, we should be able to use this effect either to measure our own peculiar velocity independently of the CMB or to constrain cosmological parameters as a new cosmological probe. Thank you.